Hello, this will be a demonstration of proposition 37 from book 3 of Euclid's Elements, which says that if a point be taken outside a circle and from it follow two straight lines, one cutting the circle and the other merely falling on it, and if further the rectangle contained by the whole of the one and the straight line interposed between the point and the convex circumference equals the square on the other straight line will be touching the circle. What we have is a point D, which we take outside the whole circle, A, B, C. And further, we have a straight line, DCA, cutting the circle ABC, and another straight line, B, merely falling on the circle, like so. And we also know that these two straight lines fall on the circle ABC such that the rectangle contained by AD and DC equals the square on DB. So AD being the whole of the cutting straight line and DC being the straight line interposed between the point and the convex circumference, and the square on the other straight line merely being the square on DB. And what we have to prove is that the other straight line, DB, touches the circle ABC. We begin by drawing a straight line which we know to be touching the circle. We'll call this the straight line DE. We do this by proposition 317. Next, we find the center of the circle ABC. We'll call that point F. We do this by proposition 3:1. And finally, we join the straight lines FE, FB, and FD. We do this all easily by postulate 1. Now, because DE touches the circle ABC at the point E, and we know that DCA cuts the circle, we can use the previous proposition, 336, to say that the rectangle AD times DC equals DE squared. However, we were also given that the rectangle AD times DC equals DB squared, and so we have two things equal to the same thing, namely the rectangle AD times DC, and so these two things must be equal to each other. And that's, in this case, that means that DE squared is equal to DB squared. This is simple common notion 1. And if squares be equal, we know that the sides of the squares must be equal as well. That's a property of magnitudes. And so we know that DE must be equal to DB. Now, what we have here are two triangles, DBF and DEF, where three sides are equal to three sides. We have just shown that DE is equal to DB. We also know that FB and FE, being radii of the same circle, are equal. It's definition 115. And we have this third side, FD, which is common to both. And so we can say that these two triangles, DEF and DBF, are equal in all respects. And the important respect is that the angle DEF is equal to the angle DBF. Now, what we know about this angle DEF is that it's actually a right angle because we have DE touching the circle at the point E. We have a straight line FE drawn from the center to the point of contact. We can use proposition 318 to tell us that this angle DEF is a right angle, which means that any angle equal to it, namely the angle DBF, must be a right angle as well. And so this angle here, DBF, is also a right angle. Now finally, using the porism of proposition 316, we know that if we have the diameter of a circle, and FB is effectively a diameter, it's half of a diameter, and we draw from its extremity, in this case the point B, a straight line perpendicular to it, we know that the straight line so drawn must touch the circle. In this case, we know that FB is a radius of the circle, and we have BD, which is perpendicular to FB at the point B. And so we can say that this straight line DB, being perpendicular to FB, also touches the circle ABC. Now, this being what we set out to prove, we are done with the proposition, therefore, etc., QED. It's the converse of the previous proposition 336. And that's all I have to say about this proposition, which means that I am done with book 3. So the next video will start book 4, naturally, at a proposition 4.1. So I will move on to that.